In this video, you are going to learn about basics of linear algebra, which are nuts and bolts of machine learning. Now, let's get started.
One of the very basic concepts in linear algebra is a concept of a point or a vector. Let us understand with simple coordinate geometry. Let's assume I have a coordinate system like this. If I have a point here, geometrically this is a two-dimensional surface, and let's assume I have a point P here. This point can be represented with two values. The first value corresponding to how far away is this point. This point is, let's say, 3 units away from origin. Origin basically here is 0, 0. So my point P has two components, x1 coordinate as 3 and x2 coordinate as 1. So this is how I represent a point. We can represent a point basically using a vector. So we can write a vector as P equal to 3, 2, which is two-dimensional vector where 3 is x1 component and 2 is x2 component. Just remember all this terminology I am using. What if I have a point in three-dimensional space? I have x1, x2 and x3 axes like this, and there is a point here, let's say Q is 1, 3, 5, where 1 is x1 component, 3 is x2 component and 5 is x3 component. That means point Q is 1 unit away from on x1 axis from origin, 3 units away on x2 axis from origin and 5 units away on x3 axis from the origin. This point Q can be represented in vector form as Q equal to 1, 3, 5. This is a dimensional, three-dimensional point, vector of size 3. What about n-dimensional point? Whatever we learn in 2D and 3D in linear algebra, we can use the same understanding for higher dimensional also. We can represent an n-dimensional point in vector form as, let's say, x is equal to 1, 5, 4, 9, 6, 15, etc. Here x has n components. We can't visualize more than 4-dimensional space, but mathematically I can write a point in n-dimensional space by using n components. This is a very simple idea of what a point is. Now let's understand the distance of a point from origin. Let's take 2D example. Suppose I have a point P here with component A and B. That means this length is A and this length is B. This is my origin. This is distance D, which is a distance between origin and point P. We can simply apply Pythagoras theorem to find out D. This length is B, this length is A. D is nothing but square root of A square plus B square. This is in 2D. We can apply the same concept to 3D also. Using the Pythagoras theorem, I can prove that the distance of this point from origin is square root of A square plus B square plus C square. We have seen distance of a point from origin in 2D and 3D. We can apply the same concept to n-dimensional also. For n-dimensional point, let's say P is equal to A1, A2, An. The distance D would be square root of A1 square plus A2 square plus An square. What we have learned in 2D and 3D, we can easily extend it to n-dimensional also. This is the beauty of linear algebra. Now let's understand distance between 2 points. Let's see an example in 2D. Then we can extend this to higher dimensional space. Let's assume I have two axes, x1 and x2, and I have 2 points P and Q. Let's assume P has A1 and A2. and Q has B1 and B2. Now I want to find distance between these 2 points. Using basic coordinate geometry, we can find the distance D, which is nothing but square root of A1 minus B1 square plus A2 minus B2 square. We can find this using Pythagoras theorem. This distance is nothing but B1 minus A1, and this distance is nothing but A2 minus B2. So using Pythagoras theorem, we can find D as square root of A1 minus B1 square plus A2 minus B2 square. Similarly, in 3D, if we have 2 points P as A1, A2, A3 and Q as B1, B2, B3, distance between P and Q, if it is D, I can simply write D equal to square root of A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. This again we can prove using Pythagoras theorem. Similarly, for n-dimensional space, if we have 2 points P as A1, A2, An and Q as B1, B2, Bn, we can write the distance between P and Q as D is equal to square root of A1 minus B1 square plus A2 minus B2 square plus An minus Bn square. Again, the same idea we learnt in 2D and 3D, we can extend it to ND. This is the beauty of linear algebra. Let's learn simple terminology and notations here. We have, let's say, vector A as A1, A2, A3, An. Here A has n components, so it has one row and n columns. So when we have something like this, we write subscript as 1 cross n. Here 1 represents number of rows and n represents number of columns. We can write A 1 cross n, which means vector A has 1 row and n columns. When a vector has only 1 row, it's called a row vector. Similarly, for column vector, if I have a vector B and suppose it has components like this, so here B has n rows and 1 column. It can be denoted by B in the subscript n cross 1, where n represents as number of rows and 1 represents as number of columns. Given a vector or given an array, I can write as a row vector or a column vector. We will see how these are useful. Here I am just explaining notations. Similarly, for matrix, matrix typically represented as A in the subscript m cross n, which means I have a matrix here A which has m rows and n columns.
Now let's see dot products and angle between two vectors.
Suppose we have 2 row vectors, A is equal to A1, A2, An and B is equal to B1, B2, Bn. Let's learn some basic mathematical operations on vectors. Addition. When I add these 2 vectors, I get simply component-wise addition. A plus B is equal to A1 plus B1, A2 plus B2, An plus Bn. This is addition of vectors. What about multiplication? There are 2 types of multiplication for vectors, dot product and cross product. Just for simplicity, we don't use cross product much in machine learning. So we will not go in details what a cross product is. Let's go and understand what a dot product is. If we have 2 vectors A and B, dot product is written as A dot B. It's a component-wise multiplication. It's nothing but A1 B1 plus A2 B2 plus An Bn. You might ask, multiplication we understand, but why addition? For now, let's define this way. We will see geometrically later. This can be written as vector notation a1, a2, an, 1 cross n, b1, b2, bn, n cross 1. As long as this and this match, you can multiply it, right? Whenever someone says A is vector, we will consider it as a column vector. This is for simplicity. By default, it's a column vector if it's not given explicitly as row vector. Let's say I have A is equal to A1, A2, An, n cross 1, which is a column vector because default representation is always a column vector which has size n cross 1 and rows and 1 columns. Now what does A transpose mean? A transpose means basically swap your rows with columns and columns with rows. A transpose is equal to A1, A2, An as 1 cross n. I can convert a column vector to row vector by just taking transpose and this becomes 1 cross n. So going back to our previous example, what we had, A dot B is equal to A1, A2, An as 1 cross n, B1, B2, Bn as n cross 1, which is nothing but A transpose B. So we can write A dot B is equal to A transpose B notation wise. This is from pure linear algebraic perspective. Now let's understand geometrically what does A dot B mean. Let's assume I have 2D space and let's assume I have vector A and B. Of course, A has two components A1, A2 and B has two components B1, B2. A dot B can be written as norm A into norm B into cos theta. Let's assume angle between A and B is theta. So norm A is nothing but length of A, which is nothing but distance of A from origin. Similarly norm B is length of B. Now this is very useful. Now if someone gives you two vectors as A1, A2 and B1, B2, how do you determine what is the angle between them? Let's quickly see that. I can write A dot B is equal to A1, B1 plus A2, B2 is equal to norm A into norm B into cos theta. That means theta is equal to cos inverse A1, B1 plus A2, B2 divided by norm A into norm B. We have seen earlier that norm A is equal to square root of A1 square plus A2 square, which is nothing but distance of a point A from origin. Similarly for point B. If somebody gives two vectors A and B, we can easily find the angle between both of them if we just know their components A1, A2, B1, B2. What if I have two vectors A and B in two-dimensional space? Let's assume they are perpendicular to each other, which means angle between them is 90 degree. So A dot B is equal to norm A into norm B into cos 90 degree, which becomes 0 because cos 90 degree is equal to 0. So if dot product between two vectors is 0, we know that these two vectors are perpendicular to each other. This whole idea that angle between two vectors can be extended to any dimensions. Here A and B can be any dimensional vector. It doesn't matter. We can't visualize more than 3D. So if A is equal to A1, A2, An and B is equal to B1, B2, Bn, we can compute A dot B using this formula, norm A, norm B, cos theta, which means we can compute theta is equal to cos inverse A1, B1 plus A2, B2 plus An, Bn divided by norm A into norm B. If A dot B is equal to A1, B1 plus A2, B2 plus An, Bn is equal to 0, then I know that A is perpendicular to B, where A and B could lie in any dimensional space. This is the beauty of linear algebra. Linear algebra and coordinate geometry are very nicely connected through relationship like this. What about A dot A? A dot A is equal to A1 plus A2 plus AN is equal to A1 square plus A2 square plus AN square is equal to norm A square, which is nothing but square of the distance. We have earlier seen that distance of a point from origin is equal to square root of A1 square plus A2 square plus AN square. Without visualizing, we can extend the idea of 2D, 3D, 2D. That is the power of linear algebra.
Now we will learn projection and unit vectors.
Let's understand a concept called projection. Let's assume I have a vector A and I have a vector B as mentioned in this graph, and the angle between both of them is, let's assume it is theta. Projection of a vector A onto a vector B is nothing but you take this vector and make it perpendicular to B, and this distance D is nothing but the projection of A on B. You are projecting A onto B, and the distance that you get on B is called the projection of A on B. We know that projection of A on B is equal to D is equal to A cos theta. We also know that A dot B is equal to sum of AI BI, where I is equal to 1 to n, which is norm A into norm B into cos theta. So if we divide both the sides by norm B, we will get A dot B divided by norm B is equal to norm A into norm B into cos theta divided by norm B. So here on the right hand side, norm B will get cancelled out. So finally we will get A dot B divided by norm B is equal to D. If we don't know what theta is, and we just know the components of A is equal to A1, A2, AN and B is equal to B1, B2, BN, we can compute the projection of A on B by using this formula, which is D equal to A dot B divided by norm B. Now let's see unit vectors. Let's assume we have a two-dimensional space, and let's assume I have a vector A like this. So A has two components, A1, A2. Unit vector is represented as A cap. A cap is equal to A divided by norm A. We know that this is the length of A as mentioned in this graph. Unit vector is a vector in the same direction as my original vector. So this red line is my unit vector A cap. Let's see the properties of unit vectors. First, A cap is in the same direction as vector A. Second, norm of unit vector is equal to 1. Since we are dividing a vector A with length of A, so the length of unit vector would be 1. These are the properties of unit vectors. We have just defined the simple terms here.
Now let's learn equation of line, plane and hyperplane.
We have learned about point or vector. Let's move ahead and learn about line. Let's look at what is line in 2D. Suppose we have x1 and x2 axes. If you recall, in our school days, we used to write line as y equal to mx plus c, where m is the slope of line and c is the intercept on y-axis. This is one equation of line. There is an other equation of line called as ax plus by plus c is equal to 0, which is general form of line, and both are equivalent. And you can prove it because by just rewriting the equation, I can write as y equal to minus c by b minus a by b into x. So here c here is minus c by b and m here is minus a by b. ax plus by plus c is equal to 0 is called a general form of line. Here if our axes are x1 and x2, then general form of equation can be written as ax1 plus bx2 plus c is equal to 0. Since in linear algebra we are generalizing concepts of 2D and 3D to higher dimensions, so general form of equation we will write as w1 x1 plus w2 x2 plus w0 is equal to 0, which is equation of line in 2D. The same notations we will use for higher dimensions. Line is a linear surface in 2D. What about 3D? Equivalent idea of line in 2D is a plane in 3D. In our school days, we have learned equation of a plane as ax plus by plus cz plus d is equal to 0. Here we have three axes, x1, x2 and x3, and if we generalize it, the equation would be w1 x1 plus w2 x2 plus w3 x3 plus w0 is equal to 0, which is equation of linear surface. This is equation of plane. So in 2D it is called line, in 3D it is called plane, and in ND it is called hyperplane. Line is called linear surface because it separates the whole region into two regions. It's linear structure. One region is on one side of the line, and the other region is on the other side of the line. Similarly, plane can separate the whole region into two regions in 3D. One is above plane and another is below the plane. You might ask, what is the equation of plane in ND? For ND, we call it hyperplane. Hyperplane. W0 plus W1 x1 plus W2 x2 plus Wn xn equal to 0. This is the equation of n-dimensional hyperplane. We can write this equation in more concise way as W0 plus summation over I equal to 1 to n Wi xi equal to 0. This is summation notation. There is a slightly more interesting way to write this equation. I can write it as W0 plus W1 W2 Wn x1 x2 xn equal to 0. This is nothing but vector notation. Here we are just changing the notation slightly. Here x is the vector which has n rows and one column. So notation wise we can write it as x n cross 1. Similarly, vector w has one row and n columns. So it can be written as w1 cross n. This is simple matrix multiplication of a row vector with a column vector. We will look at different properties of line and plane in next few videos. As I mentioned earlier, given any vector, if I write vector w, by default it's a column vector. This is just for simplicity, for notation purpose only. If I write a vector x of n dimensions, it would be column vector x n cross 1. Using these notations, w and x, which are column vectors, we can rewrite our above equation as w0 plus w transpose x equal to 0. Here we are applying transpose operation on vector w to convert column vector to row vector. This is more concise way to write an equation. Planes are typically written as pi. Equation of plane for any dimensional space would be pi w0 plus w transpose x is equal to 0. If w is n cross 1 and x is n cross 1, then this is the equation of plane for n dimensional space. Let's understand what does w0 actually mean. To understand this, we will take 2D example which is very easy to understand. So now if we write a general equation of 2D line which we saw earlier, w1 x1 plus w2 x2 plus w0 equal to 0. We can rearrange the terms here and can write it as x2 is equal to
minus w0 by w2 minus w1 by w2 into x1. Here minus w0 by w2 is nothing but c, and minus w1 by w2 is nothing but my m. X2 is nothing but y, and x1 is x. If line is passing through origin, c becomes 0, right? But c equal to minus w0 by w2. So w0 has to be 0 in general equation. Our general equation is w1 x1 plus w2 x2 plus w0 equal to 0 is the general equation of line. Suppose I have to write a line passing through origin. What would be the equation of line in 2D? My equation of line would be w1 x1 plus w2 x2 equal to 0. In 3D, equation of a plane would be w1 x1 plus w2 x2 plus w3 x3 equal to 0. For NT, equation of hyperplane would be w1 x1 plus w2 x2 plus wn xn equal to 0, which is nothing but w transpose x equal to 0. This is equation of a plane passing through origin. If it is not passing through origin, then equation would be w transpose x plus w0 equal to 0. Let's understand this in different way to interpret this equation. Suppose I have 2 points w and x in n-dimensional space. Dot product would be w dot x equal to w transpose x equal to norm w norm x into cos theta equal to 0 for a plane passing through origin, where theta is the angle between w and x. The moment w norm w into norm x into cos theta equal to 0, then theta becomes 90 degree, which means w and x are perpendicular to each other. We can also say that if w and x are perpendicular to each other, then theta is equal to 90 degree. Suppose I have a plane pi. Let's assume this is origin. Our plane is passing through origin. Let's assume this is any point x1 on this plane. Let's assume w is a vector like this, which is perpendicular to plane pi and also passing through origin. This is just for simplicity. x1 is a point on the plane. Since w and x1 are perpendicular to each other, w dot x1 is equal to 0. So for any point on this plane, if we take any point on this plane, if w is perpendicular to this plane, then w dot x1 is equal to 0, and that's what we are calling the equation of the plane. If w is perpendicular to pi, then w dot xi is equal to 0 for every xi belongs to pi. One way to interpret this equation, w transpose x is equal to 0. Suppose I have a plane pi which is passing through origin, and suppose I have a vector w which is perpendicular to the plane. This is one way to interpret what w is. W is the vector which is perpendicular to the plane at origin. This is important. Unit vector of w is nothing but w cap equal to w divided by norm w. Instead of w, let's assume I have a unit vector w. Even then my w cap into xi will be 0 for every xi belonging to my plane. Oftentimes plane is represented with a vector or with a unit vector w cap. Oftentimes it is just written as w. It represented a unit vector which is perpendicular to a plane. Here we have assumed that plane is passing through origin. For simplicity, oftentimes we assume that plane is passing through origin. If it does not, then we can change the axis and make it passing through origin by shifting axis in coordinate system. Now we will see distance of a point from a plane. We have understood the equation of the plane in previous video. Now let's understand how to compute the distance of a point from a plane. This has been used a lot in various algorithms. Let's assume I have a plane pi and let's assume it is passes through origin. We know that the equation of the plane which is passing through origin, we can write it as W transpose X is equal to 0. It means your vector W is perpendicular to this plane. We have seen this in previous video. If you have not watched that video, then please watch it. Link has been provided to the description. Imagine if there is a point P. If we are considering as n-dimensional space, then it has n components. Now I want to understand what is the distance of this point from the plane, which means I am trying to understand the shortest distance here, right? So I draw perpendicular from this point to the plane and we will find the distance d here. Here we know that W and P both are column vectors. By default, we consider them as column vectors. So here D would be W transpose P divided by norm W. This is the equation of the distance. By the way, we can prove this equation. Right now we are not proving, we will just use this formula. Please leave a comment in the comment section if you want to know how to derive this formula. Now let's assume I have 2 points P and P dash as mentioned in this chart. Here P is one side of the plane and P dash is on the other side of the plane. Let's assume the distance is d dash from the plane to point P dash. Question here is, since W is in above direction and P is also in the above direction, so vector P will look like this red arrow. Here D is nothing but D equal to W dot P divided by norm W. If W is unit vector, then norm W would be 1. We can discard this denominator because it's always 1, right? Now the angle is theta between vector P and vector W. Here the angle is less than 90 degree between W and P. So W dot P will be positive, right? Since W and P are on the same side of the plane. Remember, plane separates the whole region into 2 parts. One part is above the plane and one part is below the plane. This region is called the half space. Line in 2D separates into 2 half spaces. Similarly, plane separates 3D coordinate system into 2 half spaces. Similarly, hyperplanes creates half spaces in higher dimensional space. That's what a half space means. If you take a whole area to be a space, then half space is something that you get when you break that whole space by any linear surface like line in 2D, plane in 3D and hyperplane in ND. Now let's understand what is happening here. So D equal to W dot P divided by norm W and D dash is equal to W dot P dash divided by norm W. Since this angle is less than 90 degree, since W and P are in the same half space, so W dot P will be positive. Angle between W and P dash is this theta dash, which is greater than 90 degree, which means W dot P dash would be negative. Because what is dot product geometrically means? It is nothing but W dot P is equal to norm W norm P into cos theta, where theta is angle between W and P. Of course, what is the negative distance? It means nothing, right? Because what you do actually, when you have to compute distance between a point and a plane, is you take the absolute value. So distance would be always positive, but the sign is extremely important here because it tells me whether the point P is in which half space, in the same direction of vector W or in opposite direction of vector W. Means for all the points which are on the same direction of vector W, which is normal to the plane and passes through the origin, their dot product with W would be positive, and for all the points which are on the opposite direction of vector w, their dot product with w would be negative. Dot product is really very important in linear algebra and machine learning. Whatever we are learning in 2D, it holds true for any. Now we will learn some distance measures which has been used extensively in machine learning. Let's assume we have two-dimensional space and we have 2 points. By the way, we can extend this idea to higher dimensional space as well. For simplicity, we will consider 2D example. Suppose I have 2 points x1, y1 and x2, y2. So the distance between them is suppose d. Then here to find d, we can use Pythagoras theorem. We have seen this in one of the previous videos where we have seen d is equal to square root of x2 minus x1 square plus y2 minus y1 square, which is also known as length of x minus y. That means norm x minus y. If there is length of x, that means norm x, then we know that it is length of a point x from origin. This distance d is called Euclidean distance. It is also known as L2 norm, that means norm x minus y with subscript 2. Now let's see what is Manhattan distance. Manhattan distance. Let's write the formula. Mod of x2 minus x1 plus mod of y2 minus y1. I remember the formula like this. If you see the Manhattan region in New York City, all the roads are like grid or boxes like structure, and you can't take from one point to other point as shortcut distance, which is mentioned as green line here, because there are buildings there. So you have to take the path like mentioned as red lines. Here we are finding distance between x2 minus x1 and we are taking absolute value because distance can't be negative, right? Similarly, we are taking mod of y2 minus y1 and we will add them. So this is the formula only to find the Manhattan distance. It is also known as L1 norm, that means norm of x minus y with subscript 1. Now you might ask when to use Manhattan distance and when to use Euclidean distance. We will answer this question when we will learn classification algorithms in detail. There is something called Minkowski distance, which is also called LP norm. Its formula is norm of x minus y with subscript p is equal to, in bracket, sum of mod of xi minus yi raised to p, this whole bracket raised to 1 by p, where I is equal to 1 to n, all features. If p is equal to 1, then it becomes L1 norm, which is nothing but Manhattan distance. If p is equal to 2, then it becomes L2 norm, which is nothing but Euclidean distance. Till now, we have seen some distance measures like Euclidean, Manhattan, and Minkowski. There is one more distance measure called cosine distance. Cosine distance and cosine similarity are related terms. First, let's understand the relationship between similarity and distance. Let's take 2 points A and B. If the distance between these 2 points increases, then we can say that they are less similar. Similarly, if the distance between these 2 points decreases, then similarity between them increases. There is opposite behavior. We can say 1 minus cos similarity is equal to cos distance. Remember this formula. Now let's understand what is cosine similarity. Let's take 2D example. Suppose we have 2 points A and B as mentioned in this chart. This is my vector A and vector B from origin as mentioned in this chart. Distance between A and B here is called d, which is Euclidean distance. Cosine distance says that take angle between these two vectors. Cosine similarity between A and B is nothing but cos theta, where theta is the angle between A and B. This is how cosine similarity is defined. You can think of it like if the points are going far away from each other or angle between these 2 points increases, then both points are less similar. Here we can say cosine distance between A and B is equal to 1 minus cos theta. Now let's take another example. Suppose I have 2 points A and B as mentioned in this graph. In this case, cosine similarity between A and B is equal to cos theta is equal to 1, since angle between A and B is 0 degree here, and we know that cos 0 degree is equal to 1. So cosine distance becomes 0. We have just seen the formula of cosine distance in terms of cosine similarity, right? So cosine distance or cosine similarity uses the angle between 2 points. Let's understand some more properties of cosine similarity. This is important. Suppose point A is on x-axis. If point B is also on the x-axis, then cosine similarity becomes 1 and cosine distance becomes 0. If point B goes far away from point A, then cosine similarity will decrease. Let's say if point B is on y-axis, then cosine similarity will become 0 and cosine distance will become 1, because angle between A and B is 90 degree here. So cos theta will become 0. So cosine similarity would be 0 here. If point B is on x-axis on negative side, so angle between A and B is 180 degree in this case. So we know that cosine similarity between A and B is equal to cos theta. Here theta is 180 degree. So cosine similarity will become minus 1 and cosine distance will become 2. Similarly, if point B is on y-axis on negative side, angle between point A and point B will become 270 degree. So theta is equal to 270 degree here. So as point B is coming near to point A, so its cosine similarity increases in comparison with when angle was 180 degree. In this case, cosine similarity becomes 0 and cosine distance becomes 1. This is how cosine distance and cosine similarity works. What is the formula for cosine similarity? Cosine similarity is equal to cos theta, and we already know that A dot B is equal to norm A into norm B into cos theta. So cos theta is equal to A dot B divided by norm A into norm B, where norm A and norm B are length of A and B respectively from origin. These are L2 norms of A and B respectively, and theta is the angle between both of them. Range of cosine similarity is from minus 1 to 1. So if it is minus 1, then we can say that both the points are not similar. If it is 0, then we can say that both the points are perpendicular, and 1 represents total similarity. If A and B are unit vectors is nothing but whose length is 1. So if A and B are unit vectors, then cosine similarity is nothing but dot product. Suppose we have binary vector or Boolean vectors like this. A is equal to 1 0 1 0 1 1 1 and B is equal to 1 1 1 0 0 1 0. Hamming distance between A and B is equal to number of positions or dimensions where binary vectors differ. Here in this case, at 3 locations they are different. So Hamming distance is very interesting distance measure when we have to find distance between a Boolean or binary vectors. Hamming distance also has been used when we have strings. Suppose I have strings like this. A is equal to machine and B is equal to science. I can write the Hamming distance between A and B is equal to number of locations where the string is differ. So here in this case it is it differs for 6 locations. So Hamming distance between A and B is 6 in this case. Please note that Hamming distance only works when we have strings or arrays of the same length. This is very important.
That's it for this video. Thank you for watching. If you have any questions explained in this video, then please ask me in the comment section. If you like this video, then please click on like, share and subscribe my YouTube channel. This is Gunjan Varde signing out until we meet again.